Welcome to this first session on physics, learning, and datasets. It has quite a mixed range of papers. So we follow the same protocol as previous days, 3 papers, each 5 minutes, and then 3 minutes discussion.
Good morning, everyone. My name is Tian from UCLA. Today, I'm going to present our work, Divergence Triangle, for joint training of generator model, energy-based model, and inferential model. So our work considers the learning of 2 probabilistic models, the energy-based model and the generator model. So the energy-based model is built on the observed data X, which forms bottom-up mapping, while the generator model generates the observed X, which forms a top-down mapping. So specifically, the energy-based model specifies a probability distribution on input data through energy function that maps every input signal to a scalar. So it involves the normalizing constant and can be learned by maximum likelihood estimation, or the MLE learning. For generator model, it assumes the data are generated by latent variable z. It is a latent variable model which specifies a prior distribution as well as conditional distribution. So the latent variables are unknown and need to be integrated out to get the model distribution. And we also learn such a model by MLE. So the MLE learning for 2 models both involves the intractable terms. For energy-based model, the learning needs to sample from the model distribution, which is intractable because of the normalizing constant. And we need MC-MC sampling for approximation. While for the generator model, the learning needs to deal with the posterior distribution of the model, which is also intractable. And the expensive MC-MC steps is also needed for approximation. So the goal here is to jointly and tractably learn both models. So we propose the divergence triangle on 3 joint distribution families. It includes the generator as a P distribution, the energy-based model in pi distribution, the observed data in Q distribution. So it also includes the inferential model Q phi on both the observed data and the generated samples. The hope is that the generator model could catch up with the energy-based model, and the energy-based model could further converge to the data distribution so that all 3 joint distributions could match. So the first term of triangle functional is an upper bound of the log likelihood of the generator model. Here, the explicit inferential model Q phi is used to approximate the intractable posterior distribution. So no MC-MC steps are needed for sampling from this posterior. The first term actually resembles the variational learning behavior where Q and P are running towards each other. Further, in terms of learning energy-based model, we use the samples from the generator to be samples from the energy-based model. So no MC-MC steps are needed for sampling. So it's equivalent to consider the objective S, and the negative sign in front of the second KL indicates the adversary learning behavior. Now, the energy-based model is learned tractably. We still need to deal with the entropy of the generator, which is inside the second KL. However, this term is also intractable. Therefore, the explicit inferential model Q phi is again used to get its upper bound. Now, put the upper bound into the objective S, and we get the last 2 terms of our framework. The proposed framework offers great advantages. By introducing the inferential model, both the generator and the energy-based model could be learned jointly and tractably without expensive MC-MC steps. And such probabilistic framework also unifies several key learning algorithms together. The generator model in this framework can be well learned on large-scale datasets for objects and things, and can generate realistic samples. It could also be learned to generate high-resolution images. Finally, the energy-based model learned in this framework is also well-behaved. This can be indicated by the energy mapping results where the digits within the same energy basin belongs to the same class. So thank you for listening. If you have any questions, please come to our poster session. Thank you.
Hello, everyone. I'm Yu-Xiong Wang from CMU. I'm presenting our work on image deformation mental networks for one-shot learning. This is a joint work with my collaborators at Fudan University and Tencent AI Lab. Given a novel visual concept, such as the rare animal eye, we aim to recognize it from few annotated examples. A straightforward approach is to synthesize additional images for data augmentation. However, this conceptually easy solution tends to be often challenging in practice. While there has been significant progress in producing visually realistic images by using GANs, these images are still not satisfactory for recognition tasks. It becomes even difficult to learn GAN model from few training images. And the more important question is, do we really need to synthesize visually very realistic images for learning better classifiers? Probably not. Humans can robustly recognize objects even when the images undergo various deformations or transformations, such as ghosting, montagging, stitching, and partially occluding the images. While these deformed images are not visually realistic, our key insight is that they still maintain critical semantic information and can be used as hard examples to produce better classifier decision boundaries. There are a variety of ways to deform images. A simple approach is to combine two existing images. For example, we have an apple and a tree, and we can combine these two images to form an apple tree. But in general, how could we combine two images in a meaningful way to facilitate few-shot learning? We achieve this by leveraging a large set of labeled images of base classes and a mental learning paradigm. From these base examples, mental learning samples a collection of few-shot learning tasks. Each of them consists of its own small training and test set. In addition, from the base examples, we sample the fixed gallery images as an unsupervised image pool. We train a generic parametric combination model that combines the training images and the gallery images to synthesize deformed images so that they are useful for different tasks. Specifically, for each few-shot task, we sample a prop image per class in its training set. We select a visually similar image from the gallery set. Two CNNs are used to parse these two images, and their outputs produce a 9-dimensional weight vector. By dividing the images into 3x3 patches, we linearly combine the prop image and the gallery images using the weight vector to generate the deformed image. Combining the set of deformed images with the original training set, we create an augmented training set. This set is then used to learn a few-shot classifier. We backpropagate the gradients of the final loss on the query image in the test set and update the entire model. Our approach is general and agnostic to the choice of the mental learning approach. Here, we show some examples of our deformed images. The first row is the prop images of novel classes. The second row is a selected gallery images of base classes. Our approach learns to find visual samples that are similar in shape and geometry or similar in appearance. The third row is the deformed images, which preserve semantic information from the prop image but diversify their visual content. We evaluate our approach on the largest scale ImageNet few-shot classification benchmark. Here is the top 5 accuracy on more than 300 novel classes. We compare our approach against the baselines without using deformed images. Our augmentation strategy improves novel class accuracy significantly and consistently by up to 12 points for one-shot learning and 4 points for 10-shot learning. We further analyze the effect of the deformed images by visualizing them using t-SNE. The dot shapes represent the real images of novel classes. The star shapes represent the proper images, and the triangle shapes represent the deformed images. We compare our approach with a baseline that introduces Gaussian noise to prop images for augmentation. We can see that the generated examples are close to the prop image. In contrast, our deformed images scatter widely in the class manifold and tend to locate more around the class boundaries. This shows that they effectively refine the decision boundaries and thus improve classification performance. Please come to our poster for more details. Thank you.
Good morning, everyone. I am Jicong Fan from Cornell University. The topic of my talk is online high-rank matrix completion. We know that a low-rank matrix can be factorized into two smaller matrices. It means the information in the matrix is redundant, so we can recover the missing entries. Matrix completion has been applied to collaborative filtering, classification, and other data pre-processing problems. However, in practice, many data matrices are of high rank, so it cannot be recovered by low-rank matrix completion. In the example, 2 of the 3 variables are generated by nonlinear functions. The matrix is of 4 rank. In our work, we propose a new method called kernel factorization-based matrix completion. In the example, we randomly remove 1 entry of each column of the matrix. The first figure shows the incompleted data in blue color, where we have replaced the missing entries by 0. The red points are the ground truth. In the second figure, low-rank matrix completion failed. In the third figure, our method successfully recovered the data. Generally, we assume that the columns of the matrix are generated by polynomials. S denotes the low-dimensional latent variable. Fi is a p-order polynomial function. Then, when p is large, x is of high rank, so we cannot recover x by minimizing its rank. Let phi be a q-order polynomial feature map. We perform phi on each column of x. Then phi x is of low rank when n bar and n are sufficiently large. In the example, we see that compared to the side lengths, x is of high rank, but phi x is of low rank. In order to recover the missing entries of x, we propose to factorize phi x as a multiplication of phi d and z. Then, using kernel representation, we obtain our KFMC method. In this study, we consider polynomial kernel and RBF kernel. We solve the optimization by alternating minimization. We also propose an online version of our method for streaming data and large-scale problems. In addition, when the data structure changes with time, online method can adapt to the changes. In order to recover the missing entries of new data without retraining the models, we propose an out-of-sample extension. We generalize the method to the multiple linear models and multiple polynomial models. In this experiment, we compare our online KFMC with the 3 online low-rank matrix completion methods. In the 3 cases, the data are generated by 1 polynomial model, 3 polynomial models, and 10 linear models, respectively. We see that the recovery error of our method is much lower than those of other methods, especially when the fraction of missing entries is large. We apply the method to CMU motion capture database. The data consists of time series trajectories of human motions, such as walking, running, and jumping. We randomly remove a fraction of the entries of the data to simulate the failure of sensors. The offline method and the online method are denoted by solid curve and dash curve respectively. We see that online method outperform offline method. The reason is that the data structure changes with time. The recovery error of our online KFMC is much lower than those of other methods. In addition, our online method is at least 20 times faster than offline methods such as VMC and NIMC. That's all. Thank you very much.
So if we have all the speakers come up, do we have any questions? So I've actually got a question for the second speaker. So your data augmentation approach, at what point does that sort of cut off? How many shots or how many examples of each class do you need before your data augmentation stops being effective, or can you use it in the sort of large shot case as well?
Yes, actually, we're testing different shot scenario ranging from 1 shot to 20 shot scenario per class. So we found there are consistent improvement in this regime. Especially in 1 shot, there is as I showed, there is a 12 points improvement compared to baselines without any augmentation.
So is this augmentation approach good for large-scale learning as well, if you have lots of examples?
Yes, I think so. But the improvement seems to be marginal. The biggest improvement happens in the extremely low shot scenario. Thank you.
All right, we have a question over here.
This is for the third speaker. So in low-rank matrix completion, there are some theoretical results about when you can expect to solve a problem, when you can find global minima. Are there any kind of results like that for kernel, this kind of high-rank completion?
Not yet. Not yet, because for the kernel method, we cannot find the global minima. Actually, we have some empirical results for the sampling complexity. It's based on the polynomial model. Theoretically, we can show some improvement over the low-rank matrix completion method. More details can be found in our paper, especially the supplementary result.
Do we have any other questions? If not, let's thank the speakers again. So for the next group of 3 speakers, I think, is there one speaker missing? Do we have the speaker here for the 6th paper? Oh, you here? Okay. All right.
Good morning, everyone. I'm Tiancheng from Carnegie Mellon University. Today, we are going to talk about how to detect and recognize different powders on complex backgrounds using multispectral imaging. Well, there are many different kinds of powders in the world, like food additives, makeup, drugs, and explosive powders. Detecting and recognizing them could be useful for applications like cooking robot, criminal identification, drug control, and security checks. However, finding and recognizing those powders could be very difficult. Well, for example, in this image, there are 4 different powder samples. Can you find them? Well, even if we know where they are, it's still very hard for us to tell what they are. It's because we do not have enough useful information to distinguish between different powders and between powders and backgrounds. Algorithms may use shape, context, texture, and color information for recognizing objects. But powders have no specific shape. They can be deposited anywhere. They are textureless, and many different powders share the same color. Like in this image, 20 different powders look all white in visible light. So, to solve this problem, we propose to have a look at a wider range of the spectrum. Well, as we can see that as the wavelength gets longer and longer, the powders show significantly different appearances, especially in the shortwave infrared channels. In practice, we found that using one RGB image together with a near-infrared channel and 4 shortwave infrared channels are enough for our task. To capture such data, we propose to co-locate a RGB image with a near-infrared image, a near-infrared camera, and a shortwave infrared hyperspectral camera, and image the target through a 45-degree mirror. The spectrum of the shortwave infrared camera can be controlled by 2 voltage settings. Well, now it looks like we just need to capture enough data and train a machine learning model, right? But in practice, we found that it doesn't work. Let's see why. Here are 3 different powder samples. We can see that the powders are actually translucent, and its transparency depends on the thickness of the powder. So the thin powder on background color really depends on the powder color, background color, and the thickness of the powder. So to capture a data set covering different powders, different backgrounds, and different thickness levels, it may take me 20 years, because I need to prepare all the powder samples and backgrounds, calibrate the system, capture the image, label the ground truth, and clean the table finally. So it's not doable for me. To solve this problem, we propose to render thin powder on background images by blending thick powder and background images. We propose a model that assumes the thin powder intensity is a per channel alpha blending between a thick powder intensity and the background intensity. The alpha value follows the Beer-Lambert law. And the model parameters are very easy to calibrate using a thin powder patch, a thick powder patch, and a background patch. We built such patch dataset with 100 different powders and 100 different background materials. And we composite and blend those patches to render thin powder on background images. We also built a dataset that with real powders on real backgrounds and with ground truth labels. Here are our experimental results. And the powder names are shown on the right. Well, we first assumed that the powder location is known, and we only need to predict what kind of powder it is. And our method, based on nearest neighbor, achieved over 60% top 1 accuracy, and is actually 20% higher than the one without the blending model. And we also found that using only 4 shortwave infrared channels together with near IR and RGB can already achieve a high performance. The second experiment, we assume that the powder location is unknown, so it becomes a segmentation task. Our result, based on deep learning, is very similar to the ground truth result. And we can actually detect powders on humans, which are not perfectly static. In the future, we may consider a wider range of the spectrum, like X-ray or mid-wave IR, to achieve a higher accuracy and to detect powders behind the surfaces. Thank you very much.
Hi everyone, I'm Samarth Brahmbhatt, and today I'm going to talk about ContactDB, which is a dataset captured via thermal imaging for analysis and prediction of grasp contact. So this is joint work with my collaborators Kyusa, Ham, Charlie Kemp, and Dr. Hayes, James Hayes at Georgia Tech. So contact is a big part of our physical interactions with people, objects, and also robots, but we don't really have methods to observe and quantify contact from real-world observations. And that is because occlusion makes observing contact very difficult. In the past, researchers have used various methods. So they've captured contact with model-based tracking and proximity thresholding, embedding sensors inside objects, tactile skins in gloves, synthetic data, or through crowdsourcing. In contrast with those approaches, we capture the real contact at unprecedented detail and encode it in the texture of the object mesh. And we call these textured meshes contact maps. Here's an example with Lau et al., comparison with Lau et al., who infer the saliency map from crowdsourced labels, but we capture the real hand-object contact. So the principle is that heat transfers from warm human hands to the object surface during grasping, which can be observed through a thermal camera even after the object is let go. So we 3D print our objects to ensure consistent material properties and invite participants to the lab for data collection. And they're instructed to grasp these objects with one of 2 functional intents in mind. After grasping, the object is scanned with a calibrated rig of a Kinect and a FLIR boson thermal camera. So here's a typical data stream from the 3 cameras in our setup. And you can notice the valuable contact information hidden in plain sight, but which can be revealed with the thermal camera. These thermal images are texture mapped to the object mesh to get the contact maps. And participants grasp a set of 27 household objects with the intention of using them, and a superset of 48 objects with the intention of handing them off. And in total, we have 50 participants, so the ContactDB dataset has almost 4,000 contact maps and 400,000 triplets of RGB, depth, and thermal images from those scans. Let's look at some analysis from all this data. The first one is that the functional intent significantly influences how people grasp objects. For example, they grasp binoculars with both hands to use them, but with a single hand to hand them off. Another example is placing your thumb on the flashlight button to use it, but not while handing it off. People with relatively smaller hands prefer bimanual grasps, while those with larger hands prefer single-handed grasps. How much of the contact is actually at the fingertips? We estimated an upper bound on the fingertip-only contact area by annotating some participants' palm prints and compared that to the whole hand's contact area. Now, the whole hand's contact area shown by the blue bars here is often significantly higher than the maximum possible fingertip contact area shown by the red line, which motivates the inclusion of palm and the proximal parts of fingers in contact modeling software, which has traditionally ignored those areas of the hand. We also investigate training deep learning models to predict contact from object shape. Those models could, for example, be used for positioning the robot body and hand before grasping known objects. To do this, we actually need to learn a one-to-many mapping because there are multiple equally correct ways to grasp these objects, and ContactDB captures 50 of those ways. We adopt 2 approaches from the literature. DiverseNet appends integer-valued control variables to different CNN layers to induce diverse predictions, and stochastic multiple-choice learning trains multiple copies of the CNN. For each input, we have multiple possible ground truth contact maps, which are associated with their closest predictions, and then gradients are backpropagated to the appropriate paths. We represent the object shape as either a voxel occupancy grid or a point cloud. And our models can predict plausible contact maps for classes of objects they've never seen before, like the mug, pan, and wine glass shown here, and for new shapes of seen object classes, like the new camera and new hammer shown here. If you visit contactdb.cc.gatech.edu, you can interactively explore the whole dataset. And you'll also find links to download the dataset, code, and our trained models. Thank you. Please visit our poster for more details.
Okay, good morning, everyone. My name is Jiantao Zhou from University of Macau. Today, my paper's title is Robust Subspace Clustering with Independent and Piecewise Identically Distributed Noise Modeling. So the core work of this paper is a subspace representation, robust subspace representation. So as you know, this problem can be cast into an optimization problem consisting of 2 parts. The first one is a regularization term, capturing the signal prior. And the second term is a fidelity term, basically capturing the noise behavior. So in this paper, we propose a new and a generic noise model and use that to build up a new fidelity term, which is quite robust against the wireless types of noise encountered in a practical setting. So, okay. Okay, so basically the noise is everywhere in practice. For example, the noise could be caused by the illumination change or caused by occlusion. So sometimes the noise could be very large and sometimes it can be highly structured instead of if you assume an ID noise which is no structure. But in practice, the situation is much complicated. So yeah. actually many traditional noise modeling. For example, you can use a Gaussian noise, Laplacian noise, a mix of Gaussian noise. But all these distributions, basically, you also assume that they are IID. But in practice, in many particular noise, they are not IID. So, for example, in this very simple example, if you just use one distribution, actually you cannot generate the noise samples here. For example, the structure here, for example, there's a triangle here. And also, if you choose everything is IID and calculate entropy, all these four figures give you the same number. So certainly, this is not something we want. So we are going to propose a new noise model, which is quite generic, and we call it independent and piecewise identically distributed. So the idea behind this model is that, okay, locally we assume that it's IID, but overall speaking, it is not IID. And we use a union of distributions to capture the overall behavior of the noise signal. And we also use a partition to define the support of the local regions. And when this support is going to reduces to 1, then this IPID model reduces the traditional IID. Okay? So by using this model, we can generate a lot of structural noise as well. For example, this simple case, we have triangle structures. And we can also generate noise caused by the illumination change. So in the difficult case here, basically, this model is quite generic, can capture a lot of structural noise in practice as well. So we can say that it's a generalization of the traditional IID model. And also for this model, we can define the entropy of this IPID signal. And we also can calculate the IPID entropy from the noise samples that we have. So essentially, the idea is that we can use some weighted Poisson window, and then we calculate the distribution of the local regions, and then we summarize, average all the locations of the values, and then we can get a good approximation of the entropy value here. So here are some toy examples. The red line here is a pure IID, so you cannot see any structure. And for this blue line, basically you can observe some sort of structure. It's because of this new noise model. And also for this, the figure in the bottom, we show some comparisons with in terms of the traditional entropy and also the entropy of this IPID signal. And after you have this noise model and you can calculate the entropy, then we can integrate everything into an optimization problem to solve the robust subspace representation problem. So the only thing that we need to do here is to change the original fidelity term by using a minimization of the entropy defined over this IPID noise model. So however, this model optimizing problem is non-convex. So in the paper, we propose some relaxation algorithm to solve that. And we use that model to phase clustering, for example, and we get the state-of-the-art performance. So even though this data set is a little bit small. And also for this phase clustering, especially when you have the occlusion case, okay, so the performance gain is much larger. And there's another quite typical application of that is motion estimation. So that's the conclusion. We propose a new noise model called IPID, and then we integrate that into the robust subspace representation problem. And then we propose some new algorithms and solve that. So, well, yeah. So we also have some optimization relaxation algorithm to solve the overall problem. So all the details are on the paper, and if you are interested in the paper, you can also find us in the poster session 82. Thank you.
So we thank the speakers. Are there any questions? Okay, so for the second speaker, your data set seems to be really interesting for robotics, but one thing is what we need there is also get the bows. So I wonder, can your data set be used in any way that I actually know also in what pose the hand was and in what pose the object was?
That's a great question. Yeah, you can imagine also capturing images while they're holding the object and annotating them with hand pose. That's one way. We don't have that in our data set right now, but we have some follow-up work which shows that if you have multi-fingered end effectors for robots, you can actually synthesize grasps using this data without using any learning, just nonlinear optimization.
Okay, for the first speaker, it seems your model mostly captures the size of particles. What do you actually see in this multispectral imaging? Shouldn't it also depend a lot on the chemical decomposition or other factors?
Yes, actually size doesn't matter because powders can be any size, any shape on any surfaces, and actually the chemical components of the powders decides the spectral reflectance of that powder. So we are actually exploring this information for recognizing those powders.
Okay.
Question about that paper as well. I'm curious what effect the light conditions have on your ability to figure out which powder is which.
Yes, the night condition do affect our experiment, and in our dataset we captured four different lighting, captured our powders under 4 different indoor lighting conditions, like halogen or incandescent light, but those LED light doesn't have shortwave infrared, so we didn't use them. And if you want to use outdoor lighting, we may need to recalibrate the whole system and capture more data. Thanks.
Okay. So if there are no other questions, we thank the speakers.
So, hi, good morning. I'm Thomas Probst from ETH Zurich, and I'm going to present a joint work with Ajat Chatkuli, Dandapani Paudel, and Luc van Gool on the question, what correspondences reveal about unknown camera and motion models? So, as you all know, in computer vision, we deal with images from many different camera types, and all these cameras have different projection properties. So we might deal with image from orthographic cameras, from perspective cameras, or images formed by affine projection. However, typically when we design methods for geometry tasks, such as registration, calibration, or structure from motion, these methods are typically tailored to work with specific camera types. So in order to use them, we need to know beforehand what kind of camera we have in our problem. In the same sense, when it comes to two-view geometry, the motion between two views is typically constrained, and we also have to select an appropriate motion model. So as you see in these examples, for example, the truck is more likely to undergo a planar motion, whereas a handheld camera may undergo more complex motion. So not all the degrees of freedoms are exploited all the time, and we need to know, in order to have accurate predictions, what is the correct motion model. In particular, we are motivated by a research project we did on robotic eye surgery, where we were given images from a stereo microscope, and we wanted to perform 3D reconstruction of the retinal surface. However, in order to perform 3D reconstruction, you first need to have a proper calibration of the camera. But in order to calibrate the camera, you need to first know what is the correct camera model. So in that case, it was not clear if the camera is actually following a perspective projection, or if it's more closer to an affine projection due to the high zoom level and the high focal length. So furthermore, if you have a good prior on the motion between the views and the motion of the robot that is guiding the tool, you can have a better calibration and a better reconstruction. So this led us to the question, what can you actually tell about the two-view relationship when both the camera model and the motion type are unknown? So in other words, given only point correspondences between two views, first of all, what can you tell about the underlying two-view relationship? For example, can you tell if it's an homography or a fundamental matrix? And second, after obtaining the two-view relationship, can you actually disambiguate what is the camera model and the motion type involved? So can you disambiguate a perspective camera undergoing a pure translation from an affine camera under rotation? Regarding the first part, the problem is, in essential, you're given a set of point correspondences that is corrupted by noise and outliers, and you want to find the true underlying transformation. Typically, you would tackle this kind of problem in the consensus maximization framework. However, in that case, this would not give you optimal results, since, first of all, the model is unknown, so you don't know which model to fit. And second, the less constrained model always gives you more inliers, so it's also not clear how to select the best model. So we based our method on the assumption that the optimal camera and motion model, it minimizes the joint degrees of freedom of both the camera and the motion, and second, it should also explain a significant portion of the correspondences. We then model the camera and the motion as a set of polynomials and formulate an interlinear program to find the sparsest set of polynomials that agrees with more than half of the correspondences. The second part of our paper is then concerned with the disambiguation of the camera model and the motion type. So we summarized our work in this big table where you can look up for all the combinations of 4 camera models and 8 motion types. What is the two-view relationship that you would expect, and what kind of properties it has. So in this example, if you observe an homography of this form, you can actually tell that it is an uncalibrated perspective camera undergoing a pure rotation. And the 3 check marks indicate that you can disambiguate the camera, the motion, and the motion uniquely, as well as you can recover the motion, the metric motion. And we did this kind of analysis for all the combinations of the 4 camera models and 8 motion types. So finally, I want to show some results on relative pose estimation on the Oxford driving dataset. In this experiment, we estimated the relative pose between 2 consecutive frames without any temporal smoothing. And you can see that our method in green, which is based on the sparse motion prior, gives less noisy and more accurate results, whereas the RANSAC baseline in red gives you more outlier measurements and it tends to be more noisy. So you're welcome to our poster number 83 for more questions. Thank you very much.
So good morning, everyone. I'm presenting our work, Self-Calibrating Deep Photometric Stereo Network. My name is Boxin Shi from Peking University. This is a joint work with Ying, Chen, and Kenneth Wang from the University of Hong Kong, Kai Han from the University of Oxford, and Yasuki Matsushita from Osaka University. So we are interested in solving the photometric stereo problem. Is to estimate the surface normal of a static object from a set of images captured under varying lighting conditions. So here we need to calibrate the light intensities as well as the directions and capture the input images to estimate the surface normal using a calibrated photometric stereo. Uncalibrated photometric stereo means that we don't need to calibrate the light condition, and we estimate both the surface normal and the lighting condition. So we introduced a 2-stage framework called SDPS-NET to solve the uncalibrated photometric stereo. So the motivation here is like traditional photometric stereo, they often assume are simplified reflected model, like the Long-Burschen model. But actually in the real world, there are a lot of Long-Burschen surfaces. And recent deep learning-based method has achieved very good performance for non-Long-Burschen surfaces photometric stereo by assuming that they need to calibrate the light directions. But if we apply the latest deep learning-based photometric stereo without knowing the lighting condition, there will be obvious artifacts on the estimated surface normals as shown here. This is a method published in our ECCV last year by the same group. So the main idea of SDPS-NET is that we are adopting a 2-stage framework instead of single-stage one, meaning that we do not directly estimate the surface normal, but we estimate the lighting condition first in the first stage, and then estimate the surface normal in the second stage. There are several advantages of using a 2-stage framework. The first of the directional lightings are much easier to estimate than the surface normals because there are much fewer parameters. In this example, you can see 96 lighting directions as well as intensities. And secondly, we take the advantage of the intermediate supervision to provide a more interpretable solution. And the third advantage is that if we first estimate the lighting condition, it can be used by existing calibrated photometric stereo method. So in stage 2, we can use any arbitrary method. This is a framework of the proposed 2-stage framework. We have the LC-NET for lighting calibration and the NE-NET for surface normal calibration. So for the lighting calibration network, we cast it as a classification problem in this kind of the discretization of the lighting space. In our loss functions, we have 3 terms. The first 2 terms for the classification loss of the azimuth and the elevation angle of the lighting direction, and the third loss as the classification loss for the light intensity, and all of them are cross-entropy loss. So given the lighting calibration from this first stage, we can move to the second stage with the normal estimation. So the loss function here is very simple. This is just the popular cosine similarity between the 2 surface normals. And our framework can handle an arbitrary number of images in an order agnostic manner because we have a max pooling operation there. We train our method using 100 matter BRDFs from the Merle dataset, and we consider cast shadow and interreflection by using the physics-based mismatch renderer. And in terms of shapes, we have either the simple blobby shape and also the sculpture shape with much more geometric details. And here we show the experimental results. We evaluate on 2 different lighting distributions. One is nearly uniform, the other one is a bit biased. 4 typical types of BRDF from Lambertian to very highly specular ones. And we compare with non-learning, state-of-the-art non-learning method. And our method is robust with different lighting distribution and performs particularly well on non-Lambertian surfaces. Here is the quantitative results on the real diligent benchmark dataset, and we achieve the state-of-the-art accuracy in terms of surface normal estimation. And it's interesting to note that if we apply LCNet first and then followed by a simple linear least square based Lambertian photometric stereo, we still achieve the second best result. And here's the qualitative results on a very challenging light stage data gallery. Here the objects have very complex reflectance, and even without knowing the lighting, direction, and the intensity, we can produce very reasonably well surface normal estimation. Thanks for listening, and welcome to our poster, number 84.
Good morning. I'm John Lambert. We're pleased to introduce Argoverse, the first autonomous vehicle dataset with HD maps. Argoverse focuses on 2 core challenges, 3D tracking and motion forecasting. Argoverse is inspired by the Kitty dataset. Thousands of papers use Kitty to benchmark tasks such as 3D object detection. We've worked to create a dataset in the spirit of Kitty, but leveraging the data gathering, annotation, and mapping resources of Argo AI. Argoverse contains 3 distinct types of data. First, a dataset of sensor data from 113 scenes with 3D tracking annotations on all objects. Second, a dataset of 300,000 scenarios observed by Argo's fleet, where each scenario contains motion trajectories of all observed objects. And third, HD maps to add rich context for the 3D tracking and motion forecasting task. Let's dive deeper into each of these, starting with 3D tracking. Here the task is to determine the location of objects over time using vehicle sensor data. Argoverse sensor data includes 30 frame per second video from 7 cameras with a combined 360-degree field of view, forward-facing stereo imagery, 3D point clouds from 64-beam LiDAR, and 6-degree of freedom pose so you know where you are on the map. We collect this sensor data for 113 scenes, which vary in length from 15 to 30 seconds. For each scene, we annotate objects with 3D bounding cuboids. In total, the dataset contains more than 10,000 tracked objects. Each object is assigned to one of 17 categories, such as pedestrian, bicycle, or large vehicle. The second component of Argoverse is a motion forecasting dataset. Like human drivers, self-driving cars need to make predictions such as, will that white delivery truck up at the intersection suddenly turn left in front of us in the gap of traffic? Or what will the vehicles driving in our same direction of travel do? Will they try and cut ahead of us? Well, this black SUV seems to want to, then aborts the merge into our lane. Then finally, the driver resolves to cut ahead. To get training and test data for motion forecasting, we mine 1,000 hours of fleet driving logs and find 300,000 scenarios with interesting behaviors. Here we visualize 3 scenarios in a bird's eye view. Each scenario contains the 2D location of tracked objects over 5 seconds. Each scenario has one interesting trajectory, shown as the red dot, which is the focus of our forecasting benchmark. The challenge for an algorithm is to observe the first 2 seconds of the scenario and then predict the trajectory of the red vehicle for the next 3 seconds. For example, in the middle scenario, the task is to determine whether the red vehicle will turn left in front of our vehicle or wait. The final and perhaps most exciting component of Argoverse are the HD maps, which contain 290 kilometers of mapped lanes in Pittsburgh and Miami. The maps encode the direction and connectivity of lanes as a graph. For example, when a lane enters an intersection, the map tells you which 3 successor lanes a driver might follow out of the intersection. Here we visualize one intersection with 1 frame of LiDAR points overlaid. The maps have 2 more components shown on the right, ground height and drivable area segmentation at 1 square meter resolution. The maps can easily be projected into image space. Taken together, these maps make many perception tasks easier. For example, it's easy to filter out uninteresting LiDAR points on the road using the ground height map, even when the ground isn't planar with our lane's road surface, such as on the hill on the left of the scene. With a baseline tracker, doing ground LiDAR point removal with a map instead of a plane fitting approach increased MOTA by half a point. The map is also helpful for motion forecasting. It's easier to forecast the future driving trajectories by first inferring the lane that a driver is following. In fact, a simple nearest neighbor forecasting model that operates in a lane centerline coordinate system outperforms more sophisticated LSTM models with access to social context, but no map. We expect that there are more clever ways to incorporate these rich maps into self-driving perception tasks, but the research community hasn't been able to utilize HD maps because no previous dataset has offered them. Speaking of other datasets, we want to mention several impressive new datasets released this year. H3D, ApolloScape, and New Scenes have tracking data similar to our 3D tracking dataset. The datasets have varied sensors, environments, and annotations. Each has certain advantages. Argoverse's motion trajectory dataset and HD maps are fairly unique, though. You can download and learn more about our dataset at argoverse.org. We've created a Python API to interact with the data and maps. On the right is our map API tutorial. We plan to expand Argoverse with more data and new perception tasks. We're eager to hear feedback from potential Argoverse users. Please come talk to us at Poster 85. Thank you, and thank you to everyone at Argo who helped build Argoverse.
All right, if the speakers can come up, do we have any questions? Oh, we've got one over there.
Hi, this is a question for the first speaker. I was wondering if you have looked at other methods of model selection, in particular based on information criterion. So usually, I think to disambiguate between fundamental matrix and homography, you use, I think, the geometric robust information criterion, and why you didn't look at this, or if you have looked at this, and what your ideas are regarding this. Thanks.
Yeah, I'm not very familiar with these methods, but the idea of our approach is that you want to do one optimization that covers all of your cases. So you want to avoid that you have to do your robust fitting to all of the possible combinations of camera models and motion types. So it kind of, to avoid these heavy exponential combinations.
For the Argoverse paper, do you plan to continue expanding the Argoverse? Are we going to be swamped with data soon?
I think you'll have a lot of data to work with so far. There may be more in the future. We're planning to hopefully add some more in the future.
Perhaps you mentioned it, but are the sensors in the Argoverse data time synchronized?
So we have nanosecond timestamps for every sensor observation. So you can synchronize them yourself. They're coming at different rates. So these ring cameras are coming in at 30 hertz, and stereo cameras are coming at 5 hertz, and the LiDAR is coming at 10 hertz. So they're not perfectly synchronized with respect to all those, but it's easy to find the closest sensor observation to the LiDAR from the 30 hertz cameras.
Do we have any other questions? If not, I've actually got a question for the Argo dataset as well. So for the motion prediction, do you have scenarios where you have similar histories, but then different resulting trajectories afterwards?
Right, so you'll find each of the trajectories in a city coordinate system. So if you were to look through the 300,000, you find many of them are at the same intersection. So you could understand the multimodal nature of what happens at the intersection just by querying the other trajectories that occur there.
Okay, great. Well, let's thank the speakers again. And if the next speakers can come up.
Hello, everyone. I'm Yin from Shenzhen University. It's my honor to be here and introduce our paper, Side Window Filtering. This is the input image, and we want to filter it. And this is the result of the box filter with 10 iterations. And on the right is our set window box filter with 10 iterations. And this is the crops we get. And you can see the edges are reversed very well. So what does a traditional filter do? They include 3 steps. Step 1, center the local filter at the target pixel. Step 2, do the proximity use the neighborhood pixels. And step 3, we get the result. On the step 2, almost all the previous filters, they are working on this step. But our question is the first step is right, or do we have a better idea? So let's consider the typical edges, like these 3 edges, and we get A, B, C, D, and E, F on the edges. And when we consider edges, we can see the edges pixels are on the discontinuous pixels. So the Taylor expansion can be get on the 2 sides of the edge. And for the pixels on the 2 edges, on 2 sides of the edge, we can use a better idea to approximate the edge pixels. For the red and blue regions, so we consider to place the local filter, local window on size of the target pixel and get many side windows instead of the typical local window. But we have another question. And when the readers is different, the number of side windows are different. So please refer to the table. The details are on the right. So we want to fix the number of side windows. And so we use the blue square window instead of the red windows. So we get fixed on 8 side windows. They are the left, right, up and down, and the 4 corner windows. These are especially good at the previous, the horizontal and vertical and diagonal and corner edges. So in the side window filtering, we had 3 steps. Step 1, we set the local window on the target pixel. Step 2, we approximate the target pixel with the neighborhoods, and we get the output from the pixels which have the minimal distance with the target pixel is the output. And all of the filters proposed in the past can be used in this framework. This is the application sections. We use almost all of the filters in our framework. You can see the result and the image enhancement result with bilateral and guided filter. And this is the image denoising result. We also used it to removing the texture. The last result is ours. And the multiple structure. This is the colorization result. Use our method, we can remove the color linkage. Thank you.
Hey everyone, my name is Abi. I'm a graduate student at MIT, and I'm presenting our paper titled defense against adversarial images using web-scale nearest neighbor search. This work was done in collaboration with my colleagues from Facebook Research. So deep neural networks are vulnerable to adversarial images, which are created by adding a carefully constructed noise vector to the input, which creates an image that is imperceptible from the original one to the human eye, but it fools the deep neural network classifier. And recent work has shown that it is possible to construct adversarial images for almost any task that utilizes a neural network approach, and including object detection and semantic segmentation, which makes adversarial attacks an important problem for computer vision today. So in this work, we take a non-parametric approach to the problem. Our fundamental hypothesis is that most adversarial attack techniques move the input away from the underlying image manifold in some feature space. Our idea is to project the input back onto the manifold by calculating the nearest neighbors of the input image in a feature space and combine their individual predictions in an intelligent way to obtain the output, the correct output. The primary issue here is that we don't have a dense representation of this underlying image manifold. And in this paper, what we do is we approximate this image manifold using a database of tens of billions of images that we got from social media. So our basic pipeline then involves two key steps: feature extraction and nearest neighbor retrieval. So for every input image, we find its nearest neighbors in a billion-scale database in a feature space constructed from a CNN representation. Once we have these neighbors, then we evaluate the predictions for each of these neighbors and employ a weighted combination of these predictions to obtain the final output prediction. So, and each of these features or the predictions are pre-computed for the database so that we don't have to compute them over and over again for each image. So we experiment with a variety of different feature layers, architectures, and weighing techniques, and the effect of which we describe in more detail in the paper. But one of the results that I want to talk about is the effect of scale. So when we want to design a system that actually uses this sort of defense, then an important question would be that how many images do we actually need before we start seeing improvements? So we found that as the number of images increases, the robustness of our defense system obviously increases. However, there's a log linear relationship. So which suggests that a defense can be feasible even with a small database which has only 100 million or 10 million images. Moreover, the effect of increasing a database beyond the billion scale has marginal benefits, which also highlights the limits of this approach, because there have been papers that show that there are certain attacks that are on manifold as well. So in addition to all the other ablation studies, we also compare our method with other defenses. The few popular defenses that are existing today, a few of them operate only on the image directly, such as like total variation minimization or image quilting, whereas there are more sophisticated defenses like adversarial logic pairing and retrieval CNN, which use adversarial training in the process. Our method does not require any training, but still performs competitively, although we do have an overhead of pre-computing all features for a large number of images. And in these settings, we don't assume that the attacker actually knows the type of defense that's employed. So finally, in a true white box sense, what we do is we create attacks that assume that the attacker knows that we're using a KNN defense. So for this attack, the attacker has a separate database, which it uses to, in addition to modify our own predictions, move the image in the manifold away from the original location. So what this will do is, in addition to changing the output prediction, it would also change the neighborhoods. But what we see is that in this figure, you can see as the attack database overlap increases to 100%, the feasibility of the defense decreases. But this can be easily overcome by creating a stochastic database that randomly samples from a larger database. And we see that even in high overlap cases where you have 40 or 50% overlap, the defense is still viable, which suggests that instead of creating methods that operate on the image, we should look at data obfuscation as a viable strategy in practical settings. And and finally, we have several other experiments, ablations, and comparisons in the full paper. To find out more, please visit our poster today at 10 a.m., poster number 87. Thank you.
Hi, I'm Stefan. I'm a student from Georgia Tech, and I'll be presenting our paper, Incremental Object Learning from Contiguous Views. This work is in collaboration with Chen Yu and Linda Smith from Indiana University. Let's discuss the key characteristics of infant object learning. I'd like to start this by showing you a quick first-person video of infant play. From research in developmental psychology, we know that infant object learning consists of repetitive exposure to objects in their environment. Their visual experience is temporally smooth and inherently incremental. Due to the lack of consistent naming events by their parents, infant learning is largely self-supervised. And last, one of the prevailing views in infant psychology is that recognition of individual object instances precedes categorization. Current object recognition methods are not capable of learning in this manner, but there's been recently interesting work in incremental learning specifically. In standard incremental learning, object categories are shown only once, and the result is usually catastrophic forgetting. Showing concepts only once is an artificial task. For example, infants or robots, when interacting with their environment, rarely get to see an object of importance only once and then never again. This makes large-scale data sets collected from the internet inappropriate for visual incremental learning. Our solution to this dataset problem is to do continual learning from synthesized data. Our approach consists of a synthetic object instance dataset, Toys 200, of 3D toy objects collected from BlendSwap, for which we develop a shader for a toy-like appearance. We also build Crib, which is a synthetic learning environment implemented as a Python API for Blender that can generate unlimited data. For training data, we generate temporally smooth videos of objects rotating in front of a dynamic background. When rendering, we ensure that objects in the foreground did not appear in the background. We refer to these clips as learning exposures. For testing data, we generate random views of objects with varying scales and lighting. Now let's take a look at the results that we get when we use this new data. We take standard incremental learning algorithms and apply them in a setting where we allow repetition. Surprisingly, simply adding repetition to these standard algorithms avoids catastrophic forgetting and allows them to reach batch performance. In this experiment, we repeatedly show each object from Toys 200 10 times at random. We are evaluating versions of the end-to-end incremental learning and iCurl algorithms. These are similar algorithms that use only 3% of data as explicit memory, and a pre-trained ResNet34 as the backbone architecture. This plot shows average incremental accuracy. For example, at time step 1000, the plotted accuracy is the average testing accuracy at that point of all objects seen until then. Training the same backbone architecture results in batch mode results in this gray X mark. What's interesting is that the exposures have no particular order to them. They can be close together or far apart. And we still see this improvement in accuracy. So now we're trying to understand this behavior, and this is truly a mystery. We verify that using our dataset in standard incremental learning settings results in catastrophic forgetting as indicated by the gap between the final accuracy and the marked batch training result. Our findings for repetition also hold for other category datasets. Now I'd like to talk about a new incremental learning task that we propose. We propose a novel weekly supervised incremental learning task using our dataset. Input consists of unlabeled sequences of frames of each object, one sequence of frame at a time, and the task is learning to correctly classify the objects. This is inspired by infant play under the assumption that children know when they pick up and put down an object. For example, an infant might play with a duck, put it down, and then pick it up again. And the key to learning in this setting is successfully doing novelty detection based on the segmented visual stream available to the infant. We implemented a simple baseline novelty detector for this new task. Notice that the blue curve indicating the accuracy of our baseline is now going down. For 4 repeated exposures in Toys 200, our simple baseline algorithm gets poor performance. The purple curve showing the number of objects discovered as compared to the ground truth unique objects seen confirms that a key factor of learning in this setting is successfully performing novelty detection. We have shown that repetition makes it possible to successfully solve an incremental learning problem. Based on this finding, we also proposed a novel weekly supervised incremental learning task based on child play. The code and the data to start working on our new problem is available on our project website. For further information and discussion, please come to our poster, number 88.
questions? Are there any questions?
Yeah, I have a question for the second speaker. So this approach seems pretty related to defense GAN, and I wonder if you've compared experimentally to that, or what you think the advantages or disadvantages are?
Right. We do have comparisons with a lot of these different approaches. I guess the main difference between defense GAN and ours is that fundamentally we look at just obfuscating the data, so we don't do anything with the model. The model is available to the attacker. We just hope that as long as the exact database isn't available, it should still be robust. The thing with defense GAN is that potentially in a white box setting, defense GAN as well could be attacked in the same way, right? So that's, I guess, the key difference. Although, yeah, ours is, I mean, both of them look at some sort of generative modeling or modeling the manifold in some sense. So that is similar.
Hi, my question is for the last speaker. So you mentioned that you have a learning environment based on Blender that you've released. Does that environment also provide the ability for algorithms to pick up or put down specific objects?
Do you mean, can you essentially choose which object should come next in the sequence?
Yeah, yeah.
Yeah, so that is possible, but ideally, in the last task that we proposed, the knowledge of which object comes in the sequence is not supposed to be available. But if you want to adjust it and use it for something else, then that's also possible.
No, I mean in this context of an algorithm actively choosing to explore novel.
So it's possible to query a specific object and they get an episode with that specific object. Yes.
Thank you.
Okay, so for the first speaker, have your filters also been tested under multiple resolutions? And how much more effort is it that you have to put in by using these different shapes?
We don't test the result on the multiple resolution images. We tested them on the regular RGB images, but we will do more research on it. Thank you.
So are there any more questions? Okay, then thank you.
So this next set of speakers are the last speakers for the session. Can I remind the audience to please stay in your seats until the end of the question time. Thank you.
Hello, everyone. Hello, everyone. I'm Xiaolin Wu. The title of our work is IP102, a large-scale benchmark dataset for insect pest recognition. This is the outline of this report. It comprises of 5 parts. Globally, 1 of 9 people suffers from chronic hunger, and unfortunately, about 1/3 of crops are lost to insect pests. In addition, there will be 10 to 25% more losses per degree of global warming. This is the estimated pest-related changes in years of the major grain crops, including wheat and rice and maize. Take East Asia as an example. There are many more than 54 million tons of crops were lost due to insect pests and global warming. So insect pests is very important, and we need to accurately recognize them. In vision community, we already have some related data set. However, they still have some limitations. For example, the maximum dataset contains only about 5,000 images and cover a maximum of 40 insect pests. For the collection environment, most of them have a simple background and fixed host. But we need more data to support the deep learning technologies. We conduct data collection and annotation in 4 steps. We first establish a hierarchical taxonomy for the IP102 dataset. We then collect images for popular web search engine by name of the past. Then we have some people to preliminarily filter the raw data. Finally, we invite 8 agriculture experts to perform the data. The IP102 dataset comprises of 102 categories of insect pests. There are about 75,000 images with class labels, about 19,000 images with boundary boxes. The IP102 has a hierarchical structure. Each insect pest is assigned an upper-level class based on the crop that the insect pest class mainly damages. This is the example. Our IP102 has 2 challenges. The first is the imbalance distribution at different levels. This is the number distribution of each category. This is the specific imbalance ratio at different levels. Another challenge, intra-class variance. There are 4 forms of insect pests. All of them can cause varying degree of damage to agricultural productions. Classifying them to the same category is difficult. Inter-class variance, the pests between the classes are often similar. In this section, we present some benchmark results. For the classification task, the deep feature performs better to the handcrafted feature. We can further find the bias result between the F1 merit and accuracy. It may be caused by the imbalanced distribution of data. Classification on the level of superclasses. We can see the classification model performs well among the different superclasses, and there is a large gap between the mango and the rice. Let's analyze the reasons. The insect pests belong to the superclasses of mango are easier to classify due to the discrimination in shape, while the insect pests belong to the superclass of rice are harder to classify. The first reason is the similar color between object and the background. The other 2 reasons are the small interclass variance and the large intraclass variance. For the object detection task, we evaluate several major frameworks. The FP1 achieves the best performance. The top 2 method is the YOLO V3. It combines multi-layers of features. The first row shows some successful detection cases. There are some failure cases. Some small objects are misjudged. This is sometimes the objects are misclassified. This is the conclusion of our work. Thank you. Welcome to my poster.
Hi everyone, this is Zheng Tang. It is my pleasure to present CityFlow, a city-scale benchmark for multi-target, multi-camera vehicle tracking and re-identification. This work was completed during my internship at NVIDIA. The benchmark datasets and evaluation server are available at the AICT Challenge Workshop in CVPR this year. We had over 300 academic and industrial research teams from 44 countries participating in the challenge this year, which had grown 5-fold compared to last year. Let's start with examples of person-based problems, which have attracted many researchers' attention in recent years. Object re-identification is also known as re-ID. We are given a number of query images, and our goal is to find images of the same identities from a test set, ranked according to their similarity. On the other hand, multi-target, multi-camera tracking, or MTMC tracking, is a different task. The original videos and camera topology are provided so that spatial temporal information can be leveraged for identity association. Different from the person-based scenario, vehicle-based problems are considered more challenging. First, vehicles present higher intra-class variability, as the vehicle shapes vary depending on different viewing angles. Second, vehicles also suffer from higher inter-class similarity, because car models produced by different manufacturers look similar to each other. In summary, image-based ReID is one of the three main components of MTMC tracking. We also need to conduct multi-target single-camera tracking, or MTSC tracking, to compute trajectories within each camera. Besides, spatial temporal information between cameras can be utilized for the association of trajectories. There have been many large-scale benchmarks for person-based ReID and MTMC tracking, which turbocharged related research in this area. In comparison, only few benchmarks are available for the equally important vehicle-based problems. To the best of our knowledge, CityFlow is currently the only existing one to support vehicle-based MTMC tracking. It also includes a large number of cameras, which lead towards city-scale solutions. We also provide baseline camera calibration results to help project vehicle locations to GPS coordinates. Note that a subset of our proposed benchmark is also made available for image-based ReID. Now you can see a more detailed overview of the CityFlow benchmark. There are 5 scenarios in CityFlow, covering both highway intersections and residential areas with various traffic flow conditions. In total, we have 40 cameras located at 10 traffic intersections. The total length of all the videos is about 3 hours and 15 minutes, and the total number of vehicle identities is 666. The diversity of vehicle color and type in CityFlow is also noteworthy. For the annotation of MTMC tracking, we first run a baseline tracking by detection approach on the videos, and then manually correct errors like false positives, false negatives, and identity switches. The same identities across multiple cameras are also grouped manually. Here is a demonstration of one of the 5 scenarios. We show the same vehicle passing through multiple intersections, which was captured in different viewing perspectives. Note that the appearance of the vehicle may change significantly in different views. All the license plates and human faces have been redacted. Several state-of-the-art in-person-based and vehicle-based ReID are chosen as baselines and evaluated on our benchmark. The CMC curves of different methods are displayed in this figure. We show that metric learning-based methods perform much better. Embeddings of triplet loss, like hard triplet loss, all triplet loss, and sample triplet loss, and the combination with cross-entropy loss achieve better performance. This can be further visualized in the qualitative performance comparison. For 2 of the queries, the top 10 matches found by each method are shown. In these examples, the combination of cross-entropy loss and hard triplet loss can recover vehicle identities most effectively. This table presents the comparison of baselines in single-camera tracking and object detection. Among all the evaluated approaches, the tracklet clustering method and SSD are the most reliable ones. Finally, we add in spatial temporal association schemes to evaluate the overall performance of MTMC tracking. The manually set transition time distributions lead to high accuracy, but the transition time can also be learned reliably using Gaussian distributions. The benchmark datasets and evaluation server have been made available at the AICT Challenge workshop. To learn more details about the benchmark and the challenge this year, please find us at the poster session. Thank you for listening.
Hi everyone, my name is Amir Zadeh, and today I will be presenting our newest dataset called Social IQ, a question answering benchmark for artificial social intelligence. Social IQ takes advantage of question answering paradigm, which is a successful paradigm for creating and evaluating intelligent systems. Since the dawn of intelligent question answering in 1961, we have successfully integrated multimodal information into QA systems. But looking at the general intelligence, one of the main areas that we need to cover is artificial social intelligence. How can we teach computers to understand social situations? That is why we built our Social IQ dataset. Social IQ is designed to have to follow the same diversity as we see in online videos such as YouTube. We have social gatherings, intimate moments, debates, and discussions, certainly not limited just to these cases, but definitely just examples from the data set. But what is social intelligence? Based on psychological studies, more specifically psychometric studies of social intelligence, we define 3 main criteria for social intelligence in Social IQ dataset. At the highest level, we need to understand the social phenomena. What are the causes of the social situation? and what are the overarching characteristics of the social situation. So for example, are people getting along? How is the atmosphere in the room? An interesting challenge for understanding social phenomena is that we need to understand the causality and contingency within the social situation and also the temporal multimodal events. At an intermediate level, we have mental state and attitude. We need to understand the people inside the social situation. So for example, was the man hurt when insulted? Was the woman brave? An interesting challenge in this area is that we need to give models the common sense needed to reason and infer about individuals within the social situation. At a behavioral level, we have multimodal behavior. We need to understand the multimodal behavior. We need to understand the communications, gestures, and how people socially engage with each other. For example, how did the man show his discontent, or how did the woman respond to the rude person? Referencing is also a challenging aspect in social situations. For example, the funniest person in the room, or the woman next to the annoyed man, which clearly goes above just having the person in the blue shirt. Social IQ contains videos, questions that probe the social intelligence facets, and answers to those questions. All of these questions, videos, and answers are validated to ensure the high quality of the data set. There's 1,250 diverse videos in social IQ dataset from more than 600 channels across YouTube. There are 7,500 questions in social IQ dataset. These questions are generally challenging, around 10.8 words long, which is higher than other methods for multimodal QA. We have ranging from 5 to 25 words per question, and the top 3 categories are why, how, and what. We also validate to make sure that these questions do actually probe social intelligence facets we defined. Each question in social IQ carries 4 correct answers and 3 incorrect answers. Incorrect answers are designed to be as close as possible to being correct, while humans still detect that it's an incorrect answer. Correct and incorrect answers follows almost similar word distributions. This is something specific to social, it's a unique characteristic of social IQ dataset, which makes it harder for the models. So basically we have 52,500 answers in social IQ dataset. Social IQ is a multimodal dataset, so we want to make sure that all modalities are helpful in question answering task. We have a prediction task, binary question answering, 1 question, 2 answers, pick the correct answer. So we want to see if there's any biases within the data set. So we just give the question and the answer to the model. We get 57%, which our baseline is around 50%. We add transcript to questions and answers. It helps the accuracy. We add acoustic modality. It also helps the accuracy. But visual modality is the dominant modality for this task. And then we also implement state-of-the-art models in multimodal QA. And we observe that no model goes higher than 65%. Compare this to human performance, which is just above 95%, we see that there's a significant gap, and there's a lot of interesting research to be done in artificial social intelligence. Thank you very much. The dataset is available for download. We have the pre-processed features under CMU Multimodal SDK, and we also make our annotation system online and available. We'll have upcoming challenges. Thanks.
All right, do we have any questions for these speakers? So I guess I'll recycle a question from earlier and I'll ask it to all 3 speakers. Is the intention to keep growing the data sets that you're proposing, and are we going to see versions 2 and 3 in future years?
Yes. We will extend the dataset in scale of the data, instant number, and the categories, and the more annotations, and so on.
For the city flow benchmark, actually, the data that we release is just a tip of the iceberg. We have hundreds of hours of videos collected in a mid-sized US city, and we are planning to do more annotation and make the data set bigger and make it to be real city scale benchmark.
Yes, we're actually planning to extend to Social IQ 2, which goes in another domain, which is movies. The work has already started on that, so hopefully we'll see that soon.
Do we have any other questions? No? Okay. Well, let's thank the speakers. And that concludes the session. Thank you.